Hey guys, I'm Jed. Welcome back to my LeetCode Review One Take blog on the 39th problem, combination sum. We're given an array of distinct integers, candidates, and a target integer, target. We are written a list of all unique combinations of candidates, where the chosen numbers sum to target. We may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two candidates are unique if the frequency of at least one of the chosen numbers is different. Let's see the example 1 here. We got empty candidates 2, 3, 6, 7, and the target is 7. 2 and 3 are candidates, and 2 plus 2 plus 3 equals 7. We'll note that 2 can be used multiple times. 7 is a candidate, and 7 equals 7. There are the only two combinations here, 2 plus 2 plus 3, and a single 7. Looking at this problem, we are asked to find all unique combinations of numbers from a given array that sum up to our target value. And we can reuse numbers as many times as needed. This is a classic backtracking problem. We can think of a few approaches. Approach 1, naive recursive approach. We can try all possible combinations by adding each candidate to our current combination and recursively find remaining combinations. But this is inefficient and would create many multiple combinations. The first approach is naive iterative approach. A more efficient approach is to use backtracking with an index parameter to avoid duplicates. Backtracking with index parameter to avoid duplicates. Let's implement the backtrack approach, which has a good balance of simplicity and efficiency. First, we'll create a list to store all valid combinations we have found. And the code is list of integer called result. Gets a new empty array list. Then we'll use a helper list to build our combinations. And the code is list of integer called current combination gets a new empty array list. Then we start the backtracking process with candidates array. And this new method needs 5 parameters, which is candidates array for target, initial index at 0, current combination, and the result list. Backtrack with candidates, target, index at 0, and current combination, and the final result list. Finally, after all recursive paths have been explored, we'll return the result list. Then we need to implement the backtrack method. Let's declare the backtrack method here, which needs 5 parameters. The first parameter is an integer array called candidates. The second parameter is int integer remaining target, and third parameter is integer start index, and the fourth parameter is list of integer called current combination, and the final parameter is list of integer result. Then let's implement the backtrack method. Every good recursive method needs a base case to know when to stop. And we have two base cases here. First, if our remaining target becomes negative, this means the lost candidate we added was too large, so this path is invalid. We just stop and return. The code is if remaining is less than 0. We just return. Then let's come to the second base case, if remaining equals 0. This means we've found a valid combination that sums up to the original target. Then we'll add a copy of the current combination to our results. This is very important because the current combination variable will be modified as we backtrack. So the corresponding code is result.add of new array list of current combination. Then we'll return as we are done with this path. After base case check, we need to iterate through our choices. We start from the start index to ensure we generate combinations in a non-decreasing order, which can prevent duplicates. We create a for loop, integer I started at start index. When I is less than candidates, that length will increment I after each iteration. For each iteration, first we will need to add the current candidate to our combination. The code is current combination dot add of candidates of I. Then we pass the new remaining target, which is the previous target minus the candidate we just added. And there's one thing we have to notice. The first parameter is candidates itself. The second parameter is the new remaining target, which is remaining minus candidates we just added. And the third parameter is very important. We have to notice. We'll pass I itself as the new start index rather than I plus 1, because we can use the same number or candidate multiple times. And the fourth parameter is current combination itself. And the final parameter is the result list. After recursive call returns, we finish exploring all paths with the candidates we just added. So we must remove it from our current combination. So we can try the next candidate in a loop. So the code is current combination dot remove of current combination dot size -1. Okay, this is our implementation. Let's run it against the test cases. Yes, it got accepted. Then, let's break down the time and space complexity. First, let's say n is the number of candidates. N is the number of candidates. And t is our target value. N is the smallest number in a candidates array. Is the target value. And m is the smallest candidate. Then let's analyze the time and space complexity. For time complexity, the maximum depth of a recursion tree can be at most t divided by n, because we can't add a number more times than that without exceeding the target. And at each node in the decision tree, we have up to n branches to explore. So the overall time complexity is roughly big O of n to the power of t divided by n. Next, for space complexity, if we don't count the space needed for the final result list, the space complexity is determined by the maximum depth of the recursion stack and the size of the current combination. And as we mentioned before, the longest possible combination will be t divided by n. So the overall space complexity is big O of t divided by n. Alright, this is the end of my LeetCode review vlog on the combination sum problem. And I highly recommend you guys to visit my GitHub page here, which contains all the problems, initial thoughts, different approaches with very detailed code and comments, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the code and notes to build this online GitHub page. I'll put those two links on my YouTube description below. Thank you guys for watching. I'll see you next time. Bye bye.